Okay guys, let's take a look at today's lesson. We are actually doing 2 days of applications. This will be day 1. Today we are just going to look at 2 different kinds of applications. One is exponential growth and the other one is exponential decay. So those are the 2 types we'll be working with. On day 2 we work with some more different types of applications. So let's just kind of focus on just a few at a time. So for exponential growth, we have an equation here, and they're using n to be population. You don't have to use the letter n if you don't want to. It doesn't matter to me which variable you use. You could use p for population if you wanted to. That's fine. But this is the format of the equation. So this is our population at time t. N sub naught would be our initial population, and t would be for time. R is relative growth rate or relative rate of growth. This is a vocab word. This word pops up in calculus talking about growth rate. So it's a pretty important word that we understand what it's talking about. It's basically the rate of growth of whatever it is you're dealing with. So that's R. And in this particular case, it's expressed as a proportion of the population. So that's our exponential growth equation. So it's E, the initial population, times E to the RT. Decay, if you compare these 2 equations, they are identical. It's just that decay has a negative in the exponent, whereas growth does not. That's the only difference. This is in terms of m for mass. Again, it doesn't really matter to me which variable you use. You could use m for mass or whichever. So this would be the mass remaining at time t. M naught is in the initial mass, and t would be time. Now, in particular, so some exponential decay formulas are half-life, and some are just regular decay. So if we have a half-life formula, there's actually a formula that will determine what R is. We could just use that formula to find R if we have a half-life. It's ln 2 over h, whereas h is what the half-life of the substance is. So, for example, if we had, let's say we started out with 30 grams of something, and the half-life was, 10 years. Okay, let's say you didn't remember the formula. It's okay. What you would do is you would, if we know that in 10 years we'll have half of this left, right, we would say 15 equals 30. I'm filling in this spot and this spot. E to the, and I don't know what R is, but I know that t is 10. And then I could solve for R. I could do it, and I'm still going to get ln 2 over, 10, whatever it happens to be. I'm going to get this particular quantity. So we could do that as well. So if you forget it, it's okay. You can do it this way, solve for R this way. Okay? But it's pretty handy to remember, then you don't have to go through that. I mean, it doesn't take that long, but it's pretty handy to remember. And I think it's interesting, it's ln 2. It's a 2. And that has to do with half-life. It's a 2. So at any rate, ln 2 over h, and h is our half-life. Okay, so let's, of course, as you know, it's impossible for me to do one of every kind of problem you'll ever see. I picked a couple of them. We have a lot more different types on your daily work. So let's kind of go through these and see how we do. So the first one, we have, let's see, a population. The current population is 4,100. And it was introduced 8 years ago, and the relative growth rate is 55% per year. What they're telling us, what they're giving us, is they're giving us R. Right? R is 0.55. Typically R would be a decimal, not a percent. So if they give you the relative growth rate as a percent, you would need to turn it into a decimal. So they're telling us what R is. What we don't know is what the initial size of the rabbit population is. So what we're going to have to do is we're going to have to fill in this information in our formula, and this is a growth, right? We're not going to have the negative up there in the exponent. So the information we have is, let's see, right now we have 4,100, around 4,100 rabbits. We don't know the initial population. We don't know what that is. E to the We know that our R is 0.55. And in this scenario, there's around 4,100 rabbits, 8 years, in 8 years, right? So our T would be 8. So let's talk about the work that you're required to show. And again, everything that we do is preparing you for calculus. I mean, since the beginning, since the first math classes you've taken, that's why you have to show work. You have to show work because you don't get any credit on the calculus test if you don't show any work. If you just write answers, well, even if they're the right answers, it doesn't matter. You're not going to get any points. So that's why we've been showing work forever, right? I mean, when has your math teacher ever said you don't have to show work? Right? It's always. So I'm telling you the minimum, the bare minimum you're going to have to show. You have to show the equation. Every time you have to show the equation. Once I have the equation written, if you just want to jump to the answer, that's fine. Or you can show some more work to get to the answer. But you have to show the equation. That's the non-negotiable. So there's my equation. I'm actually going to show a little bit more work just because my brain thinks that way. I need to kind of do it algebraically, process it that way. So I'm going to solve for N naught. So that's going to be 4,100 divided by e to the, and 0.55 times 8 is 4.4, e to the 4.4. So then I would put that in my calculator, and N naught is like 50.33709. Okay, so that, let's talk about that for a minute. We had a lengthy discussion about N naught in the previous class. So let's talk about that. So N naught is our initial population. Well, this is just an estimate, right? Do you really think that on the island there are exactly 4,100 rabbits? I mean, what would the chances of that be, that there was an even number like that? I mean, the chances would be astronomical. I mean, there's probably, who knows how many there are, but that is just an estimate. So we're just going to use our initial population as an estimate. We're going to go with 50 because we really don't like thinking about portions of rabbits, or I don't. I'm thinking about total rabbit, right? A total rabbit. There's 50 rabbits. Now, some students really wanted to put the 50.33705 in the equation, in the original equation, but why? This is just an estimate. If they had told you, given you the estimate of rabbits, do you think that they would have given it to you in this kind of exact form? No, I mean, look at this. They didn't give it to you in exact form. They gave you this, right? So if we were dealing with a quantity, a substance like, I don't know, so oil, a liquid or something, we would probably keep this there. But it really doesn't make any sense for our initial population to be 50.33709. Okay, so we're going to make the initial population as 50. We're going to make that N naught is 50. And that's what we're going to use in our equation. Because this is just an estimate, right? We're just estimating. This is not exact, not an exact science. They are estimating everything. Probably a pretty good estimate, but it's not going to be correct down to the exact number of rabbits, right? How would they even do that if they're all spread out over the island? I don't know. So hopefully you're comfortable enough and it doesn't bother you, because it was really bothering the students earlier. I really want to use the 50.33709. Please don't. Just leave it as an estimate of 50. We're going to have 50, rabbits. That's where we're going to start with, is the island 8 years ago started with 50 rabbits, and now they have around 4,100. So that's our first answer. We got 50 rabbits. Okay, so estimate the population 12 years from now. Now we need to kind of think about that. 12 years from now. This word is important because our equation was created from 8 years ago, right? We created this equation starting 8 years ago. So if they're asking for 12 years from now, what is our t-value going to be? Is our t-value going to be 12? No, it's going to be 20, right? Because it's from now. The equation is written from 8 years ago. So we're going to do N of 20. So again, the non-negotiable is writing the formula. You have to write the formula. The formula is 50, so we're sticking with 50, okay? 50e to the 0.55, and we wanted 12 years from now, but again we said that that's 20 years from the beginning of the equation. So we use that. So this is what you have to write. You have to write that part. Now you can go straight to the answer once you've written the equation. So N sub 20 is 2,993,707.086 is what the calculator gives us. But we would just truncate it, just truncate. And really the thought of 2,993,707 rabbits is like overwhelming. That cannot actually, I mean, how big is this island? You know, I don't know. That doesn't seem like that's realistic, but that's what the equation generated, because this is an exponential type of equation. There are other types that we could use, like logistic growth, but that's not what this is exponential growth. That's what it's assuming. So we would come out with 2,993 rabbits, 993,707 rabbits. 12 years from now, that would be the estimate if our equation held true. Okay? So how are we with the exponential growth? Is that okay? Okay. So the next one is a half-life problem. So we have a particular substance has a half-life of 140 days. Our sample has a mass of 300. Now it wants us to find an equation that models the amount of the sample remaining at time t. Really classic problem at time t. They just want you to come up with the formula, right? The formula with the t in it. So let's do that. We'll use the m for mass, m of t. So our initial quantity is 300 milligrams. It's e to the, now this is a decay, right? It's a half-life. It's shrinking. So my formula is a negative RT, right? And we know if we remember our little formula, R is going to be ln2 over H. H is our half-life. And in this particular case, our half-life is 140. So our R would be ln2 over 140, and then we have a t. So that's our function that models the remaining time for that substance. Okay, we okay with that? Now, I like keeping ln2 over 140. I like using that. It's the exact quantity, and my calculator recognizes that the exact quantity. I would recommend that you do that. If you want to turn it into a decimal, I guess it's okay, but you can't round it. You would not be able to round the decimal at all. You can't round into the very end of the problem, or it causes huge issues. So I really would recommend, to me, it's easier just putting ln2 over 140 than some decimal that I may copy incorrectly. Okay, so I would just recommend that you leave it. You can do what you like, but please do not round into the end. It makes a significant difference in your answer. Even if you were to go out 5 decimal places, it still would be a different answer than what I get if I leave the whole exact number in. Alright, so we want to find the mass remaining after 1 year. Let's see what our equation is. Our equation is written in days. So I'm not going to put a 1 in for t, right? That wouldn't make any sense, because our equation is written in days. So I'm going to have to put 365 in for t, not a 1. So the mass at 365, again, non-negotiable is writing the formula. You have to write the formula. 300 e to the negative ln2 over 140 times 365. Okay, so I wrote the formula. Now I can put it in my calculator, and I get 49.237 milligrams. So that's the quantity remaining after 1 year. We okay with that? Okay, so how long will it take for the sample to decay to a mass of 200 milligrams? So what they're giving us a quantity, right? A quantity. So our quantity is what we put here. Yeah, so we would need to put 200 equals 300 e to the negative ln2 over 140 t. Okay? Here, I do want you to do a little bit more work rather than just writing the equation and putting the answer, because this is a bit more intense than these, right? We can do a little bit of work. We would divide by 300, so that would give me 2/3 equals e to the negative ln2 over 140t. Then, to get the t out of the exponent, we would ln both sides, right? So I get ln 2/3 equals negative ln 2 over 140t. At that point, you can just write the answer. All we need to do is divide, right? ln 2/3 divided by this, and we'll get our answer. So this is as far as I need you to do work. You could continue if you would like, but that's as far as I need you to go. So when we divide that out in our calculator, we get 81.895 days. Please be sure you go to the thousands on everything except living things, right? Living things you would truncate, not round. And like money, let's say you had a problem with money. You really wouldn't want to go to the thousands with money. You would treat money like money, right? We go to the cents with money. So we would go to the hundreds with money. Okay, but everything else you need to do thousands. That's our standard. Okay? How are we doing? All right, great.